Okay, let's talk more about induction. All right, so in this chapter, we're going to talk about electromagnetic induction and how it's used in technology. So let's talk about how it's used in technology. So you may have rolled up to a traffic light that is not on a timer, right? It kind of waits for a car to arrive and then the light will change shortly after. And you may have wondered how this works, and you've probably seen like lines in the asphalt, and you probably maybe thought it was a weight sensor or something. I don't know if you ever think about that. I did. And then when I took physics, I realized that it is not a weight sensor. It is an induction sensor. So how does this work? There is a coil built into the asphalt. And this coil has a current flowing through it. And when you roll your car up over it, which is a piece of metal, right? It's essentially a hunk of metal. That current that's flowing in the conductor that's embedded in the asphalt, it's going to produce a magnetic field. And that magnetic field is going to enter your conducting car, create a change in flux, induce its own current, which then produces its own magnetic field that influences the circuit that is embedded in the asphalt. So there's a lot of back and forth. The back and forth is B field, current creating another B field creating another current, back and forth, back and forth. Okay, so the current changes in the circuit embedded in the asphalt because of the presence of the car, the conducting car. And that's essentially how the traffic light sensors work. So we're going to talk about that back and forth. Okay. That back and forth is called mutual inductance. And so let's consider a simple case of two coils of wire. Okay, these are just this is just like solenoids, right? You have a current carrying wire, you curl it into a cylinder, okay, really tightly. That's essentially what these are. Okay, we're just looking at half of them. We just cut it in half, looking at half. And so we have two different coils. They're near each other. And let's send a current through this one. Okay, this will be coil 1. So the current flowing through coil 1 is I1. Well, anytime we pass a current through a conductor, we're going to produce a magnetic field. Okay, and because this is a coil shape, the magnetic field is going to go through the center of the coil. And if we place another coil nearby, like this one here, it's going to feel that magnetic field. And if that magnetic field is changing in time, a current will be produced. Why? Because of a flux change. So this flux change that occurs will then produce a current in this coil. Where's purple? Here's purple. Right? We'll produce a current in this coil, I2. And then that current will create another magnetic field, okay? And that magnetic field will change the flux of this one and send another current this way. And it goes back and forth, back and forth. That's what I mean by the back and forth. But we're only going to consider basically two directions, because every time you go back and forth, the field is not as strong, right? Because the current is smaller. So it drops off really quickly, and we stop caring about the terms, the third order and the fourth order and the fifth order terms, okay? We're just going to care about one to the other, okay? Coil 1's influence on coil 2, or coil 2's influence on coil 1. So we already know how to figure out what I2 is. We figure out I2 by using Faraday's law. Faraday's law says that the voltage in the circular voltage, right, through coil 2 is equal to the number of turns of coil 2 times the change in flux through coil 2. All right, that's Faraday's law. And let's kind of like break it down a little bit. What is this? Well, this is B created by coil 1 through the area of coil 2. Okay? What is B? Do we have an expression for what B is? We do. That was in chapter 28, B due to a solenoid, mu naught I times, or I guess mu naught little n I, okay? Where n is the number of turns per unit length. So it's basically B is proportional to I, right? So B is proportional to I. And what we can do is, there's a bunch of constants in front of it. We can lump all these constants into M, to this constant called M, which we will name the mutual inductance. And we'll put N2 in there as well, okay? And then we can restate Faraday's law as the voltage through loop 2 is equal to this constant M times the change in current with respect to T. Okay, so all we did is we substituted B into the flux change. Since the area is not changing, we pulled it out. We pulled out all these other items that aren't changing with the time. The only thing that can change with time is the current, and that's right here. Okay, and then all those other constants are in the M. And so basically what we've shown is how to determine the voltage through coil 2 due to a magnetic field created by current flowing through coil 1. Okay? So this mutual inductance, there's some other cute algebraic things you can do, all right, to isolate M. And when you do that, we can figure out what the mutual inductance is by just knowing the number of turns in coil 2, the flux change through coil 2, and then the current through coil 1. And then you can switch all those subscripts around and determine that same mutual inductance parameter. Okay? That's why it's mutual, right? It's mutual. So the inductance created by a current flowing through coil 1 is going to be the same as the inductance created by a current flowing through coil 2 and its influence on coil 1. The unit of mutual inductance is the Henry, okay? It's a Weber per amp, right? Weber per amp. There's a lot of other ways to describe it, but not important, right? Weber per amp is probably the most important. And so let's talk about another application of mutual inductance. I think a more everyday one is wirelessly charging your phone, right? If you have a newer phone, it may have wireless charging where you have like a place to dock your phone. It's typically like a circle, and you stick your phone on top of it. Well, a wireless toothbrush, electric toothbrush operates on the same principle. And so basically, this part is connected to the wall, which sends in an AC current, right? A current that changes with time. That current changes with time, flows in a circle, creates a magnetic field in and out of the page. You put your phone on top of that, which has its own circle in the back. That changing field produces a current and a voltage in your phone. And then that's the power that charges your phone. Okay, so mutual inductance is used in wireless charging, wireless sensing of conductors, like we saw with the traffic light. A lot of uses. So let's do this example. And this example is kind of like a derivation as well. So we have two coils, and they're coaxial. Okay, so they share the same axis. And one has length L, turn, number of turns N1. So this is going to be coil 1. And then this will be coil 2. And we're given the area of coil 2 and its length. The question is, what's the mutual inductance? What's that M value? Okay, so we can start this by applying one of these equations here. Let's go ahead and use either one of these. Well, which one do we have the most information on? Looks like we have the most information on coil 1, right? Because we have its area and its length. So let's use this guy. Okay. And so the mutual inductance is going to be equal to N phi over I. Oops, let's use a different color. Let's see, so N2 phi through coil 2 over I1. Okay. And, I think we were going to use the other one. We could probably do either way. Let's do them both. So let's start over here. Well, we know the number of turns for coil 1 is N1 turns, so we don't need to manipulate anything there. What about phi B1? Let's expand what that is. Phi B1, well, that's BA, right? That's the magnetic field where's the magnetic field coming from? It's coming from the other coil, so I would denote that as B2, the magnetic field created by coil 2, through area 1, through the area of coil 1, and the area vector and the B field vector are parallel, so I'm dropping my cosine theta, I don't care, it's 1, divided by the current flowing through 2. Well, now we can expand this further by figuring out what is B2. Well, B2 is the magnetic field generated by a solenoid. B2 is mu naught little n times the current through that coil. So our subscripts then, so mu naught little n is the number of turns per unit length, okay? And the current flowing through coil 2 is I2. Then we divide that by I2. Oh, oops. This should be N2, right? This is the magnetic field generated by 2, which would be N2 I2. Okay. Sorry about that. Right? Because the second coil is generating the field that coil 1 is feeling. Okay. So we have all that in there. We can cancel some things out. Let's rewrite it. Mu naught, N1, N2. The I2s cancel, and then my L goes down below. So what we see is that the mutual inductance is equal to a bunch of geometrical parameters. Mu naught, the number of turns in the first coil, number of turns in the second coil, and the length of the first coil. Okay, so that's basically another form of the mutual inductance that can go along with this equation up here. We're basically just expanded what phi was in terms of the magnetic field created by the other coil and the area of the first coil. Okay, so let's read this sentence or these sentences, all right, to fully solidify the idea of mutual inductance. So you have a current flowing through one coil. That current causes a magnetic flux through another coil. How much flux that is caused in that other coil by the current is determined by M of the two coils. M doesn't depend on the currents, only the geometry. Okay? That's mutual inductance. So in this example, we're kind of going to put some numerical values here. We're going to use the same setup as before, where we had a long, skinny coil, and then we had a larger coil wrapped around it. And suppose that the current in the outer coil is given by this. Times T, okay? So that's the time varying current. And so you may have noticed that we have switched over to lowercase. Anytime we use a lowercase variable, that's going to be a time-dependent variable. Okay, so anytime you see lowercase, think a time-dependent variable. So that's the current through coil 2. The question is, at t equals 3 microseconds, what is the average magnetic flux through each turn in coil 1 due to the current in coil 2? So what are we asking for? We are asking for the magnetic flux in each turn through coil 2. Nope, coil 1, right? The average flux through each turn. So I imagine that means the flux divided by the number of turns. What is that? So we are also given, which isn't stated in the problem, we're given, right, in this scenario from example 30.1, we're given some dimensions, right? We're given the length of coil 1, the area of the cross-sectional area. We're given the number of turns. And so we need that information in order to find what M is so that we can find out what this is. So where can we find out what this is? So let's look back at our equations. We want to know, like, what's phi B1N1? Phi B1N1. Well, it looks like I have phi B1N1 right here. Okay, so all I need is I2 and M. So let's start with that equation. So M equals N1 B phi B1 over I2. So we know that this okay, and we're given I2, so that's good. We know we need to start with this equation. And M, if we plug in all those values it gave us, we see that M is 25 microhenries. N1 is 1,000 turns. And we're given I2. So what we need to find is N1 phi B1. So, oh, you know what? I think I divided it, but if I'm interpreting, I believe we need this value. Is this the average through each turn? Because, right, what I'm seeing here is we have this number. So multiplying M and I2 will give me N1 phi B1. Oh no, we do. Ignore this. I interpreted it correctly, right? It's through each turn. So the each lets me know that we're dividing by each turn. So let's find, right? Divide by N1. Divide by N1. Let's find what phi B1 is. And that's going to be 25 microhenries. The current is a time-dependent current, but it's asking us at t equals 3 microseconds. So we'll plug in t equals 3 microseconds. Oh, that's a +6. I don't know why I wrote. Oh, no. Sorry. I had that right. This is a 2, right? This is the current. We're plugging in I2 here. That's 10 to the 6 amps per second times t, where t is 3 microseconds. Okay? And then all that's divided by N1, which is 1,000 turns. So we can get rid of this. We have 2 times 3, which is 6. 6 times 25, which is 2,025? 225? No, 250. 150. Mental math is not working out. Let me write it down. Oh, times 6. Okay, yeah, 0, 3, 12, 150. Where 1,000 came from. So that's 150 micro Webers divided by 1,000 turns. That's going to be phi B1. So it's asking for the average flux through each turn. It should be that value right there. We can, of course, check the answer. Let's check the answer. If we need to divide by 1,000 or not. Basically, I'm checking what is my interpretation of average flux through each coil. We need to establish that. Okie dokie. We are not getting any. Oh, you know, I can just look at the book. I was reading an academic article on pre-lecture assignments, and guess what? They are proven to improve learning in engineering education, okay? So you're welcome for those assignments. I was just checking myself and making sure it was made sense to assign those, and if they are in fact helpful, I would be happy to hear your feedback on that if you had any, if you wanted to email me for future students. So I was going to the book. Where are you, book? Let's go check out, where are we? We're chapter 30, of course. I think we're in the second. Okay, yeah, okay. So 10 to the minus 7, yeah. So there we go. They wanted I2 over N1. Okay, great. They wanted phi B1. That's what we did. Okie dokie. So 150 times 10 to the minus 9. Well, that's the same if I move this over 2 decimals. That's 1.5 times 10 to the minus 7 Webers, which is what we saw here. Okay? So not too bad, right? I mean, you know, intuitively, it's a little, you know, you got to keep track of which coil is causing the field, current flowing through which coil, so on and so forth, right? Mathematically, it's really plug and chug, okay? But you just have to, you know, plug in the right values for the, you know, watch your subscripts, in other words. Okay, so the concept here is, you know, when the current in a coil changes, it changes the magnetic flux, right? And anytime you have a changing magnetic flux, you have an induced EMF. So the mutual inductance of the two coils determines how much EMF is induced in one coil for a given rate of change of the current in the other coil. So it's basically doing Faraday's law, right? We're basically doing Faraday's law, except we're not really going to consider flux anymore. We're going to just consider the changing current, okay, in a second coil that's creating the field. So we're just replacing, we're still doing Faraday's law, but we're making a substitution. Okay, we're making a substitution for B in flux, where B is the B field created by a solenoid. Okay, which is mu naught I, let me write this over here. Mu naught little n I, well, let's do little I because it changes with time, right? Where little n is the number of turns per unit length. All right, so that's all we're doing. We're just substituting B in the flux. We're still applying Faraday's law, but now everything is going to be in terms of changing current instead of field. So it's the same discussion, but we're kind of like focusing on a different aspect of it. So, well, currents flowing through coils, solenoids, if you will, they can produce a field, and that field will produce a current in that same coil itself. Okay, you don't need a second coil there to see inductance. This coil that has a changing current produces a field in the center of it, and that field will produce its own induced current in that same circuit, right? Because anywhere you have a field that's changing with time, you will have a flux change, and thus you will get a current. Doesn't matter if it's two coils next to each other or if it's just one inducing an EMF in itself, okay? Anytime you have a changing magnetic flux, you will have a current induced. And therefore, we can describe the self-inductance of a coil. And it has the same form as mutual inductance, except now we're talking about the same coil, so the subscripts are gone, okay? It's simply the number of turns in the coil times the flux through that coil, and then the current of flowing through itself, okay? So we can change the geometry a little bit. So let's do this example where we calculate the self-inductance of a toroidal solenoid. So you may be wondering, what the heck is a toroidal solenoid? Well, recall like a regular solenoid where we had a symmetry of a straight line, and we would wrap the coil around the cylinder, right? And then when we sent a current down those coils, you do the right-hand rule where your thumb is in the direction of the current and you keep, moving it in a circle and curling your hands in. And what you find is that the B field goes straight through the center of that solenoid. Well, in a toroidal solenoid, instead of the symmetry being a, straight line, we are wrapping the coil around a circle, okay? It's a circle, but its cross section is like a rectangle. So it's like a ring, maybe is a better term for that. So we're now wrapping, I should have used purple earlier. So now we have our ring, and then we are wrapping our wire around the ring, and the current is still flowing down the wire in little circles, but now the magnetic field is still along the yellow line, but that magnetic field is, roughly in the shape of a circle, right? If we zoom in there, the tangent is straight, obviously, but the magnetic field points this way. Okay? Still a straight line if you were to unfold the ring, but now it's in a ring. So anyway, this is just a different kind of solenoid. So let's figure out what the self-inductance is. So the self-inductance is N phi B over the current flowing through that wire. And so for us to figure out what the self-inductance is in this particular arrangement, okay, the arrangement of a toroidal solenoid, we need to plug in certain values for B and A that make up the flux. So if we rewrite that over here, number of turns, and then the flux is the magnetic field dotted with the area, right, over the current through the wire. So the question is, what is the magnetic field of a toroidal solenoid? And what is the area that this magnetic field is penetrating? So we kind of skipped it, but it's in the book in chapter 28. There was a section called Applications of Ampere's Law. And in that section, we apply Ampere's Law, which we didn't focus on, to figure out what the magnetic field is of this toroidal solenoid. And so this is the result right here. I just pulled it from the chapter in the book. So the magnetic field of a toroidal solenoid is mu naught, number of turns, current through the wire, over 2 pi r, where r is the radius of the ring that we wrapped the coil around. So, so that's what we're going to plug in for the B field. And now the question is, well, what area is this B field penetrating? The area is going to be perpendicular to the direction of the magnetic field. Why? Because the area vector is perpendicular to the area itself. So we saw over here that the magnetic field vector in a toroidal solenoid, travels along the ring, right? So the magnetic field is going to be going through here, right? Coming out of here. And at every point, tangent or, I guess it's a tangent point, right? At that magnetic field position, the area here is perpendicular to it, and it's the area of this cross section of the ring. So the cross-sectional area was given to us here. Okay, so that's just A. And the radius R is this radius. So where does that come into play? Well, that comes into play here with what the magnetic field is. So let's plug in everything. So number of turns in the toroidal solenoid is N. The magnetic field of the toroidal solenoid, mu naught, another N, I over 2 pi r. And then we have the A, so it's just the cross-sectional area A, and then finally we have the current down here, I. So some things are gonna cancel, not a lot. Mu naught N squared A over 2 pi r. This is the self-inductance of the toroidal solenoid. So the procedure here is that, we expanded what phi was. We needed the magnetic field that the toroidal solenoid produces, and we needed the cross-sectional area. We needed to identify what area to use in this situation, and that's going to be the area that B is perpendicular to, right? Because the area vector of A is perpendicular to, the face of A. All right, so that's example 30.3. Let's talk about some more applications of these things, okay? Inductors, that is, the things being inductors. So you may have looked at some power lines and you look up and you're like, what are these like lumpy things attached to the wires? Okay, why are they there? Well, those are inductors. And their purpose is to absorb sudden changes in current, okay? So if lightning strikes a tower, a transmission line tower. There's going to be a sudden spike in the voltage and the current. And in order to keep that spike from flowing down the line, okay, to your house, blowing crap up, okay, in order to stop that, we put inductors there to absorb this rapid change in current, okay? And that's because inductors, the only time you get a voltage produced in an inductor is, when you have a change in current, okay? And the voltage that's produced is going to be in the opposite direction of the change in current. So if the change is increasing, you're going to have a negative voltage. If the change is decreasing, you're going to have a positive voltage, okay? And so that's going to negate any changes, sudden changes in current that occur when lightning strikes. So inductors oppose and suppress any rapid changes in current. That is their job. And what are inductors? Inductors are simply current carrying wires wrapped in a coil configuration of some sort, okay? So let's talk about putting these inductors in a circuit where we can, control and measure current and voltage quite easily. So the only time it makes sense to have an inductor in a circuit is if your circuit has a time varying current. And in this circuit shown here, we, instead of like a battery, we have like a little knob that allows you to just change the current value to whatever you want, okay? So if we were to measure the potential difference between the terminals here, well, since they're in series with this inductor, we can relate them to the inductor by Faraday's law, right? Which stated that the EMF is minus L di dt. And since we're going to be defining VAB as positive, that's why we just dropped off the positive or the negative sign. So, okay, that's the form of a voltage, L di dt. What now? Let's compare. Let's compare an inductor to a resistor. So you may recall how to find the voltage across a resistor, right? You're simply applying Ohm's law, V equals IR. So this potential is going to be equal to the current flowing through the resistor times the resistance itself. And this potential is going to get smaller as you go from left to right. What happens if you instead put an inductor in place there? Well, if you have an inductor in place of a resistor and the current flowing is constant, that means that the change in current with respect to time is 0. Well, if you plug in a 0 here, you will get no voltage, right? The only time an inductor does anything is when you have a changing current. So if you have a constant current, a current that is not changing with time, you will not get a voltage across that inductor. But now, let's say that we have an increasing current. Let's say that we're ramping the current up slowly. So if the current is increasing, well then di dt is greater than 0. And if di dt is greater than 0, we have a positive number here, we have a positive number here, and the potential is going to be decreasing from left to right The EMF produced, however, opposes that, will point in the opposite direction. So the E, that's where the E comes from, right? That's the voltage produced by the change in current. The voltage in the circuit is VAB. The voltage produced by the inductor is E, which is going to be minus VAB. Right? Because remember, this is just Faraday's law. Faraday's law states that anything that's, any voltage or current that is produced by a change in flux opposes the change. So this EMF is opposing that change, right? So it's going to point in the other direction. So now let's look at a decreasing current. Okay? The EMF is going to oppose the decrease by adding more voltage in the same direction. So your EMF will point in the same direction. Okay? Your EMF is going to be pointing in the same direction as the decreasing current. Okay? Leaving you with a negative voltage as measured in the circuit, but a positive EMF since this guy is less than 0. Okay? So the final section that I want to talk about that will be tested on in the final exam, which is not comprehensive, by the way, is the energy stored in a magnetic field. So you may not realize it, but fields, like electric fields and magnetic fields, they store energy. All right? And before we talk about that, let's talk about an object that does not store energy. A resistor does not store energy. Anytime you pass current through a resistor, if you are touching that resistor while the current is passing through it, that resistor is getting warmer and warmer because energy is being dissipated through heat. Okay, it's not storing anything. It's simply a dissipator of energy. You cannot recover that energy back. All right, once something is heated up, that heat that escapes into the surroundings is gone. You cannot get it back. It's like you cannot put the toothpaste back in the toothpaste bottle. So, however, in contrast, an inductor, you can store energy in an inductor. Okay? And we can understand that by looking at an integral, if that helps you understand anything. So if we integrate, right, this current, and it's changing with time. So we want to find out all the current values that it experiences as it changes from one value to another. Okay, let's say it goes from 0 to I. Well, how much current has actually passed through L? How do we figure that out? Well, we integrate I from 0 to I. That becomes I squared over 2. Okay, that is the energy stored in an inductor. So magnetic fields, which are creating this change in current, right? Remember, changing current creates a changing magnetic field, which itself creates an induced current. Those are storing energy and delivering it back into the circuit as an induced current. Okay, so an inductor with current I stores energy. We can describe this energy as a density, okay? It makes more sense because the energy in inductor is actually stored in the field of the coil, right? And the coil is not a 0-dimensional or 1-dimensional object. It's a 2 or 3-dimensional object. So it makes more sense to describe the density of the energy in that object in the same way that we talked about energy density between the plates of a capacitor. So the energy density per unit volume is given by little u, and that's equal to B squared, magnetic field magnitude, squared over 2 mu naught. If you're interested, in the derivation of that, we can do that. Look at the book, but this is just, this is the equation, right? And that's, if there's a mu naught there, that means it's in vacuum. So that's the energy density in a vacuum. If, however, you are in a object, okay, in a material, you would instead use the permeability of the material, mu, which is similar to the permittivity of a material. Except now, the permeability of a material, that describes how easily a magnetic field flows through that material. Whereas permittivity, epsilon, right? Remember that guy? That described how easily an electric field, right? This is a different epsilon, not EMF. Okay, this is, I guess what they did is they were using maybe this epsilon, capital epsilon. This is the permittivity. There might be a spelling mistake there. How easily an E field flows through a material. Permeability, how easily a B field. Okay. So I'm going to stop there. This part of chapter 30 is what we will be covering on the final midterm, okay? Everything else in chapter 30 and chapter 31 will not be included in the midterm, okay? It's just optional information. You may encounter it one day, you may not, okay? So that's where I'll stop here for the lecture material that will be on, tested on the final exam, okay?